This is 9-1, reflections. Hit pause so you can try the warm-up problem and hit play when you're ready to hear the answer. Numbers 1 and 3 are both a reflection over the x-axis, and 2 and 4 are a reflection over the y-axis. And I used my arrow notation there so you could see how it's mapped out. An isometry is a transformation that does not change the shape or size of a figure. Reflections, translations, and rotations are all isometries. Those were the ones that we learned in the last section. So those three all keep the same shape or size. Once we get to a dilation, later on in this unit, that's when you'll see a size change. So they're also called, another word for isometries is congruent transformations, because it's keeping the same, or rigid motions. So a reflection is a transformation that moves a figure by flipping it across a line. The reflected figure is called the image. A reflection is an isometry, so the image is always congruent to the pre-image. So it's asking if number 1 is a reflection or not in example 1, and it is not a reflection because it's not the flip of it, it's the same exact image right next to it. If it were the flip of it, there would be a line here and not a line here, if that makes sense. Okay, and so that's our explanation. And then in number 2, it's a yes. It is a flip across a symmetric line, so across this line right here, it's a flip, and it kept the same shape and size, so that is a reflection. So first I'll do, oftentimes we are reflecting over an x or y axis, and so that's our line of reflection. So we would say reflect across the x-axis, reflect across the y-axis, etc. And sometimes there isn't a line, there isn't an axis that's a line of reflection as seen below. So it says draw, example 2, draw the reflection of the triangle across the line. So I'm drawing the reflection, a mirror image of this triangle. So it would look something like that across that line. The second one there was a little bit harder to reflect, but I think I got it close enough. Example 3, 2 buildings located at A and B are to be connected to the same point on the water line. Where should they connect so that the least amount of pipe will be used? So you want to reflect the shortest distance point, which is point A. So I'm going to reflect that. Let's call that A prime. And where these intersect, where the other point B and the A prime intersect with the water line, that is where they should connect, so the least amount of pipe will be used. So basically we're saying that A prime B plus A prime is the shortest amount, those line segments, I guess, that's the shortest amount of pipe that will be needed. So the next word problem is very similar. We're going to reflect B because it's closer to the reflection line. And we can see that right here where we're intersecting, I'll put an X right here. That's where they should, where the trail should meet the river. There are 3 types of reflections: a reflection across the x-axis, across the y-axis, and across the line y equals x that we're going to focus on. And I really like the mapping statements. I think that they're the most helpful. So if you reflect across the x-axis, the x is going to remain the same. It's the y that changes because you end up dropping either from a positive to a negative or a negative to a positive usually. So it becomes the opposite sign. I mean, definitely when you go over the axis. Okay, and then across the y-axis, the y stays the same, but you're flipping left or right, so the x value will be positive or negative. And then across the line, y equals x. For that, you're actually just switching the order. X, y becomes y comma x. So if you had like 1 comma 2, it would become 2 comma 1. Okay, reflect the figure with the given vertices across the given line. So first we graph 2, negative 1. And I always write the letters, so that's letter x. Y is negative 4, negative 3. And z is 3, 2. And I can draw my shape. And it's telling me to reflect this over the x-axis. So I find that challenging to do just by drawing. I can't always visually see it, and that's why I really like the mapping statement. So if I know that reflecting over the x-axis is going to keep the x value the same, and it's only going to change the y to the opposite sign, then I can actually write all of my new ordered pairs. So x prime, the 2 will stay the same, and the negative 1 is going to become positive 1. Y prime, the negative 4 will stay the same, and the negative 3 will become the opposite sign, 3. And then z prime, 3 will stay the same, and 2 becomes negative. And so I can go ahead and graph these now. So x prime was at 2 comma 1. And you can see now that that did reflect over this x-axis, but that would have been harder to do without having done the coordinates. So I like to memorize these mapping rules. So y prime is going to be negative 4, positive 3. And z prime is 3, negative 2. So here it is, flipped over the x-axis. You might be able to see it now. It's a little bit tricky. Okay, reflect over the line y equals x. So remember, for this one, the mapping statement says that if we have an ordered pair, it just switches, it becomes y comma x. So r was negative 2, 2, and r prime is going to be, oops, I already messed up. Switch those, 2, negative 2. S prime will be 0, comma 5, and t prime is going to be negative 1, comma 3. So I'm just switching the order of the x and y values. Sorry, so first I'll do my pre-image, which is negative 2, 2 is r, 5, 0 is s, and 3, negative 1 is t. And then my r prime, 2, negative 2, and s prime is 0, 5, and t prime is negative 1, 3. And that's what that will look like.